Now, one thing that's, of course, utmost importance to practitioners is basically I know I can afford, let's say, 100 particles, m equal to 100. That's what I can do. I cannot, like a mathematician, play around and say, okay, let's make m go to a million or so, asymptotic limits, all nice for mathematicians. But so then the picture really changes. So you're in a non-asymptotic regime, and we really try to understand this as a dynamical system with 100 particles. And then you want to know, is that stable? Is that, and you're not, I think a lot of applications in data assimilation, we talk about Bayesian inference and all this sort of stuff. But in reality, all we do is some sort of shadowing. We try to stay close to the truth. And so, yes, we get some sort of statistical information about it, but it's obviously very limited. And the most important thing is that the whole thing is stable and has some sort of accuracy. And accuracy basically means that, that at least you do better than in the observed quantities. Your analysis has a smaller error than just using the observations, right? And statisticians have found various measures of doing this, scoring functions. And one that I find quite useful is this continuously ranked probability score. But I guess that's maybe not something we want to go into great detail. But there's ongoing research work, and I think it's a very important topic, to understand the behavior of these filters when you basically fix the ensemble size to a number and then say, can I show anything about that? Again, some references. We have done some work, and I'm not going to talk about it because it's a bit technical, where we actually been able to show that yes, this filter, ensemble Kalman filter, stays in the vicinity of the reference solution if the measurement errors are small enough, essentially. In that limit, you can show, and then ensemble size can be finite, essentially. And Pierre Moral in France is working on similar things, Andy Maida. There's also a wonderful paper by Brian Hunt, actually from a couple of years ago, who looked at the Lorentz system, and he used the fact that it's a hyperbolic system, so it's a chaotic system. And he even showed that 2 ensemble members are sufficient to track the reference, because the dimension of the attractor is so low in this case. And so these are an understanding we're trying to develop in why this method works so well in these extreme settings. Okay, so how do we time-wise? Is there a quarter past is a break again, right? Or is there?
We have 20 more minutes for this.
Okay. So how do you feel? I mean, I think I think it's reasonable to take a break now, and then I probably have another half an hour, maybe maximum 40 minutes, and then be done for the day. But of course, we can also, I mean, there's time for some questions.
Yeah. So after your lecture, we have hands-on.
Yeah, so exactly.
So
yeah, right. Yeah.
Save for time for questions.
Yeah, so if you got questions then on this part, yeah. We're covering a lot of ground, yeah, I understand that. So anyway, but I will be around, so if there are any questions, then just ask me. Okay.